Okay, again, good morning, everyone. We will cover today the mesh analysis, the second analysis, one of the strongest analyses that we will be learning in this course. We've seen in last lecture nodal analysis. Today we will cover the mesh analysis. So in mesh analysis, the difference here would be looking at those meshes, and our variables, as we will see, would be currents assigned to those meshes. In nodal analysis, our variables were the voltages at the nodes that we identified as distinguished nodes. Here in the mesh analysis, our variables are the currents that we will be assigning to those meshes. So at the beginning, we need to decide on the meshes that we will be using. Then we will be assigning variables. Those variables are currents, I1, I2, IM, the number of the independent meshes that we will define. And if you recall, we said that the number of the independent meshes would be B minus N minus 1. So we can say here, for example, that this M, which is the independent, and again, here I'm talking about a circuit that does not have current sources. So here we will be looking at those number of independent are B minus N minus 1, where N, we said, are the number of the nodes and B are the number of the branches. So as we will see later on, and this circuit, for example, if we are to count the number of the nodes, then I would say A is 1, B 2, C 3, D 4, E, and F are all the same node. So here I have this as one node. I have this one as a node, and this one as a node, and this one as a node. So here in this example, the number of the nodes are 4. The number of the branches, count the elements that are confined within those nodes. I have 1, I have 2, I have 3, I have 4, and then I have 5. So I have 5 branches. So we can look at the number of the meshes as 5 minus 4 minus 1, which is 2. So I need to pick 2 meshes out of the 3 meshes that I have here in general. And if you recall, we said that we can look at this A, B, E, F as a mesh. So we have here, I can say mesh number 1, mesh 1 is A, B, E, F. I can
Yes, sir.
say mesh number 2 as B, C, D, E, B, C, D, E. And I can also say that I have a third mesh, mesh number 3, as the bigger one, A, B, C, D, E, F. A, B, C, D, E, F. Now, in this example, we have picked 2 meshes out of those 3, and I said that I1 here, this mesh number 1 and mesh number 2 are the 2 meshes that I will be adopting in solving this problem. So that's why I assigned this variable that is a current to this mesh, and this variable I2 as also a current in this mesh. So what does this mean when I say those mesh currents are my variable. I am assuming that this I1, small I1 here, is the current that goes in this mesh. So this I1, this is the current that goes in this mesh. So whenever I have a branch that is not shared, this means my little I1 here, my variable I1 is going in this branch. So if I am to look at, see this capital I1 and this little I1 are in the same branch, this means that this capital I1 equals to this I1. So as if I am giving, I have two names for one entity. So this current that is going into this mesh that is called I1 small, I have another name that's called I1 capital in this branch by itself here. This means that this capital I1 is the same as this small I1. We have, yeah, yeah. I mean, well, we haven't covered the mesh analysis yet in the problem set, so now we're covering. But let me explain that further. So if I have this circuit here, the one that we were referring to, R1, R2, and R3 with two voltage sources. So I have here a voltage source. So again, if I have here a voltage source and I have here a resistor, I have a second resistor here, and a second voltage source, right? So if this one is R1, this one is R2, and this one is R3, and this one is V1, and this one is V2. Now, remember, what did we say about assigning the mesh currents? I came here and I said, well, I have two meshes here. I need to pick two. So I said, I will pick this one. I'll make it a bit bigger. I'm going to call this one now I1, which means that the current going in this mesh is I1. And I will call this one I2. So those are my two variables, I1 and I2, right? Now notice that this I1 is going solo in R1 and going solo in V1, which means I only have I1 in V1 and I1 going in R1, right? Exactly. It looks like a loop. It is the same of the KVL that we have talked about last time. However, now it's defining a current. This means here I have a variable that is a current going in this mesh. Now let's look at, just wait a second. Wait a second. There are current, yes, and they will be looked at as a KCL here, but as we will see later on, the way we write it as a KVL based. But just wait a second. This is a KCL whenever they have a shared branch. But for the time being, let's look at this I1, small I1 that is going in this whole mesh, which means I1 is going into V1 and I1 is going into R1 and I1 is going partially into R3. Now let's go to the second variable. The second variable is I2 as well. And this I2 is going in R2, only I2 by itself. I2 is going into the V2 by itself. and it is going partially into R3, right? Going partially into R3. Now, in this case, when I write my KVL equations, I will write my KVL equations such that KVL at the mesh number one, I will write it as long as this current is entering the negative, I will write this as minus V1. That's why I said it is KVL based. Now, this I1 is entering into R1, so I will write it as R1 I1, right? And this I1 is also entering into R3, so I will write it as plus R3 I1. However, you have to pay attention now to here. Look at the direction of the current. The direction of the current I1, which is where I am writing the KVL right now, is going clockwise for R3 going from up to down, right? Look at I1. I1, when it comes to R3, going from the top toward the bottom. So since I am writing the mesh equation for I1, the direction of I1 is my reference, is my positive reference, which means going from up toward down is my positive reference. Now let's look at I2. Looking at I2, I can see that I2 is going in the opposite direction. Look at I2, going from the bottom up. That's why when I write the KVL, taking I2 in the consideration, I write it as minus R3 I2, and then equals to 0. Okay? So this is how we write the mesh equation. Number one, we decide on the meshes that I need to assign variables. Number two, I draw those meshes with an arrow defines the direction, and then I assign them variables that are current. Those are currents, right? And then I write the KVL. For the components that I1 is going through, I write them as positive. So that's why I wrote R1 I1 plus R3 I1. Now, when it comes to the other variables that are sharing some components, like R3, for example, in this case, I look at the direction of I2. Is it in the same direction of I1? If it's in the same direction of I1, then I write it as positive. If it's in the opposite direction, then I write it as negative. So this is how I write the mesh equation for mesh number one. Now, if I want to write the mesh equation for mesh number two, I take the KVL at I2. Now, notice what's going to happen now. Now, I will be writing the mesh equation for I2, which means that the direction of I2 now is my positive reference. So in this case, I can see that I2 is entering the positive, and that's why I will, I will, I will. So I will write here, entering the positive, I write it as V2. And then right away, all the components that I2 are going through, I'll write them as positive. So I have here R2, I2 plus R3, I2. Now it comes to the other variables that are sharing R3. Is it going in the same direction of I2? If it's yes, then I write it as positive. If it's no, then I write it as a negative. So looking at R3, I can see that I1 is going in the opposite direction. That's why I will write it as minus R3 I1 equals to 0. Now, if I am to rearrange those two equations, so if I am to call this one 1, 2, so from 1, I will rearrange such that I have here R1 plus R3 I1 minus R3 I2 minus V1 equals to 0. And then I have R2 plus R3 I2 minus R2 plus R3 I2 minus R3 I1 plus V2 equals to 0, right? Okay, so those are the two mesh equations that we have talked about. Now let's look at the case where, now one more thing. If I want now to have I1 and I2 not in the same direction, we'll look at an example here. So take the same V1, V2, R1, R3, R2. Now, if I take this one going in this direction, and I take this one going in this direction, I2, then if I am to write the KVL at I1 would be minus V1 plus R1 I1 plus R3 I1. Now, here it comes to R3. I need now to add the contribution of I2. Look at I2. It is going in the same direction as I1 in R3. So I1 is going this way. I2 is also going this way. And in this case, because they are in the same direction, then I will add them. R3 I2 equals to 0. Right? Now, if I take KVL at I2, I have I2 entering the negative of V2, so I'll write it minus V2, and then plus R2 I2 plus R3 I2 now comes to the I1 that is sharing R3. Because it's in the same direction, then I'll write it plus R3 I1, and this equals to 0. Now rearranging, this is 1, 2, so from 1, I have here R1 plus R3 I1 plus R3 I2 minus V1 equals 0. I have R2 plus R3 I2 plus R3 I1 minus V2 equals to 0. Now, those are the two mesh equations for that circuit. Okay. Now let's see your questions. Okay. Any question?
Sir?
Yes. Go ahead.
So basically, a mesh is a loop, basically, an enclosed loop.
Yes, it's a loop that we can assign a variable has no zero current. The directions, it could be given, it could be left up to you to decide what direction you want. Again, the direction of the current, we have talked about that. We have taken the convention that the direction of the current is the opposite to the directions of the electrons flow. So we have the current going from the positive toward the negative, which defines the holes, actually, the directions of the holes. Yes, yes. Okay. So is this clear? This is how we write. But again, I'm showing here, I have shown you how to derive the mesh equations. Now we want to come to a point where we can write the mesh equation by inspection. And this is the beauty about it, if you understand. So this is the proof to you that mesh equations are being derived this way. But there's a shorter way to write the mesh equations that we call it writing the mesh equations by inspection. As long as you understand how did we derive those mesh equations. So any other question before we move on to the mesh equations by inspection? So we will do the mesh equations by inspection after we talk about the introduction of the current sources. Now, when I have a current source, this is going to affect the mesh equation. How? Because if you look at this circuit here, this circuit has three resistors, a voltage source, and a current source. If I am to assign the mesh variables, the mesh current variables to those meshes, I would be assigning them as you can see here, I1 and I2. However, however, if I look at I2 and the current source, basically I can conclude that my variable I2 that I have just assigned to this mesh is indeed equals -5. In other words, whenever I have a current source in the mesh, and this current source is not shared by the meshes, by other meshes, I can right away say that this variable that I have assigned to this mesh is now constant, is known. So I2 is not variable anymore. Why? Because I am saying here, my variable I2 that's going in this mesh, however, I have a current here that is already defined and going this way, and my I2 is going in the opposite direction. Okay, in this case, I2 now is known. Yeah, that's a typo. So I2 here is is minus 5 ampere. Okay, I'll fix that later on. So this is how current sources are affecting. If you recall, this is similar to what we have seen in nodal analysis when we had a voltage source connected between the reference and one of the variables, right? That variable became known. This is now a similar case, but in the mesh. If I have a current source in the mesh, that this current source is not shared with other meshes, then the variable assigned to this mesh becomes known. But you have to pay attention to the directions. If the directions agrees, then the variable will be positive. If the direction is in the opposite direction, then the value becomes negative. So this is what the current source is going to do to my mesh equation. And as you can see in this case, my mesh equations have been reduced. So instead of writing two equations, now one of the variables now becomes known. I only need to write one equation for this mesh number one. Okay. Now let's go to the mesh analysis by inspection. Let's go back to our example. If I have this circuit, V1, V2. Now I will give this one I1 and this one I2. And I will write them as the following. At the beginning, 1, assign the variables, the mesh currents, to my meshes, variables. 2, find the resistors that this mesh current is going through. So here, for example, mesh number 1, what do I have? I have R1 and R3. So I will go right away and as mesh 1, I have R1 and R3. Then right away I will go R1 plus R3 multiplied by this I1. Then I will look at the shared resistors. If I have a shared resistor here, R3, if the direction for I1 and I2 for R3, don't say both are clockwise, then they have to be added. No, look at R1, look at R3, the shared resistor. How is I1 going through R3? It's going from the top to the bottom. How is I2 going in R3? Going from the bottom to the top. So they are going in opposite direction, then you put minus R3, I2, and then you look at the voltage sources. If they are entering through the negative, you write them as negative. That's it. Let's do mesh number 2. Again, look at the resistors that I2 is going through. They are R2 and R3. So right away, you add them, R2 plus R3 times I2. Look at the shared, yes, they're going in the opposite direction. So right away, minus R3, I1. And then look at the voltage sources. Is I2 going in the positive? Yes, going into the positive. Then we write it as plus V2 equals to 0. This is how you write mesh equations by inspection. So here, find the resistors that this mesh current is going through, add them, and multiply them by this mesh current. Find the shared resistor. There could be more than one. You could have, for example, two shared components, as we'll see later on, the shared resistors, and look at the direction of those mesh currents through those shared resistors. If they have the same direction, then the sign is positive.
Sure.
Yes.
Is it okay if we use a slightly different convention, but it turns out to be correct anyway? Like I typically use a voltage source as positive and and you subtract a voltage across each resistor because it's a drop. So instead you could say V1 minus I1R1 minus I1R free minus negative I2R free equals 0.
Now, let's first finish, putting a convention that everyone would be able to use, and then we'll look at your case as a special case. So this will reduce the confusion among the students. So right now, let's agree upon a convention that everyone can use, and let's leave those other approaches like yours, for example, as something to look at later on as maybe another way. But let's, for the time being, instead of throwing many conventions, let's agree upon a convention, and then we can discuss yours later on. Okay. So here we said that if they have the same direction, then the sign is plus, otherwise minus. And then for if it enters, if the mesh current enters the positive sign of the voltage source, we write it as positive. So this is how we can write the mesh equations by inspection. And as you can see, it becomes very convenient and very quick. Now, if you compare those two equations, you will see that they are the same. They are the same equations that we have derived earlier using the KVL approach. Any other questions about how to write the mesh equations before we move on? Now, the super mesh here, if you recall in nodal analysis, we had what's called super node, and we said that that super node is when we had a voltage source between two nodes that none of them is a reference node. In this case, this voltage source will create a binding equation, binding expressions between those two nodes. In the super mesh here, I have a similar case, however, it's a bit different in a way that I have a current source, but this current source now is shared between two meshes. So what does this current source do? Now, this current source, as we will see here, if you recall, this is the first mesh, mesh number one. We have a mesh number two here. What's this current source is doing? This current source is creating a binding expression as well between both mesh currents. Remember when we said that I1 here is going in the 2 ohm in this direction because I1 is going clockwise. Same thing here, I2 going clockwise, but it will end up that is going in the opposite direction. So what does this mean? This means if I am to map those two I1 and I2 with the 6 ampere, I have a current source giving 6 ampere going up in this direction. This means I should write an expression here. This expression says that this 6 ampere is indeed the difference between both mesh currents, which is I2 minus I1. Now, some of you would say, well, where did you come up with this expression? Why is it I2 minus I1? Why it's not I1 minus I2? I would say, if you apply KCL right here, remember I1 is going this way, right? And I2 is going this way, and the 6 ampere is going this way. If you write a KCL here, entering our negative, then this would be minus 6 minus I1 plus I2 equals to 0. And this is going to give me I2 minus I1 equals to 6. And this is what I have just shown here. Okay? So this is the binding equation, the binding expression between both mesh variables, I1 and I2. Why? Because they have a current source that they are sharing. So once they have a current source that is sharing, I would call now this a super mesh. So what do I do in super mesh? In super mesh, where I have a current source that is being shared by two mesh currents, I would eliminate that branch, right? And merge those two meshes into a big mesh. And then I have to decide on a direction here, I will take the direction as the direction of both. But this is going to be crucial if I have I1 and I2 are in opposite direction. So, but now since both of them share the same direction, which is this direction, then things should be okay. So if I want to write the mesh equation for this, now super mesh, I call this super mesh because they had a current source that being shared, and now I have removed this current source, but this current source created this binding expression between my two mesh variables, I2 and I1. So in this case, now if I am to write the mesh equation for that super mesh, I would write it this way. Let's do it by inspection. So super mesh, I look at the resistors that are shared by I1. So keep in mind, keep in mind that I1 is only 6 ohm has only I1, and 10 ohm has only I2. So keep this in mind. So you have a separation, some kind of separation here, right? So here in this case, I will write them both in one equation. So minus 20 plus 6I1 plus 10, 14, I2 equals to 0. So this is the super mesh equation. Notice that I still have two variables, I1 and I2. Here where this binding equation now can help me solve for those two variables. So this binding equation basically says that the current I2 is greater than I1 by 6 ampere, right? The current I2 is greater than I1 by 6 ampere. Why? Because this current source created this binding expression. Any question about the super mesh? Okay, so if you want to continue solving, here we have the solution. This is the equation that we came up with, the super mesh equation. Rearrange that equation, get this. The second equation that we talked about, that is I2 minus I1 equals to 6, or I2 equals to I1 plus 6. Now, if you take this one, I2, and substitute it here and work out the equation, you would get I1 equals to minus 3.2 ampere, and I2 is 2.8 ampere. Any question about how to write the super mesh equation and how to solve it? We have several examples.
Sure.
Yes, go ahead.
So basically, to create the super mesh, you can take this part where you've removed the 2 ohm resistor and 6 amps, you cut it in half. For the first resistor will be I1, and I2 will go for the second two. Sorry, the last two.
I cut. What do you mean by cut it in half? No, I maintained my borders. I understood that based on this branch that I have removed it from here. So I need to keep in mind that the mesh current I1 is taking care of the left part of the super mesh. The mesh current I2 is taking care of the right part of the super mesh.
Well, that's what I mean.
Yeah. However, they have to be written in the same equation.
So you write it as a loop equation
You write it
or
as
a
the loop.
mesh equation.
You write it as a loop equation, keeping in mind the mesh equation. Write it as a mesh equation, exactly the same thing we did earlier. However, you keep in mind, where are you? What part are you in? Remember when we, in nodal analysis, we had a super node, we were jumping between the sides of the super node from one side to another side, where we have two variables that are binded, right? We finished the first part, and then after we're done, we went to the second variable, second voltage node within the same mesh, within the same super node. Here we're doing the same. We are on the left part of the super mesh. We write the mesh equation exactly the same way we wrote the conventional mesh equations. And then after we have finished the first part, we move to the second part, and we wrote the continued wrote writing the mesh equation for the second mesh current. So on the left part, I finished I1, the mesh equation related to I1. On the second part, I continued and then finished the mesh equation related to I2. Okay? Any other questions? Okay, so let's look at this example here. Here in this example, we don't have current sources. We have two meshes that were given to me, and I need to find the current I1, I2, and I3 using the mesh analysis. Okay, so where are those currents I1, I2, and I? Those are those capital currents. Those are localized currents. Basically, this is I1 is the current only in this branch, right? So this is I1 only in this branch. This is I2 only in this branch, and I3 is the current in this branch, right? So those are not the mesh currents. Those are currents. This branch has a name. This branch has a name for has a current, and this branch has a current. Our mesh currents are different, as we have seen earlier. Our mesh current I1 goes into the whole mesh. Sometimes he goes solo by himself, no other currents that are sharing with him. Sometimes he shares, like 10, for example, the 10 ohm. I1 and I2 are sharing the I1 and I2, the mesh currents are sharing the 10 ohms. However, the mesh current I1 is going by himself into the 5 ohm. The mesh current I2 is going by himself into the 6 ohm and the 4 ohm. Okay? So those capital I's are different than my small letter variables I1 and I2, right? Now I need to find those capital I's, I1, I2, and I3 for that circuit using the mesh analysis. So let's start first by writing the mesh equation number one. Mesh equation number one. Who wants to give me the mesh equation number one by inspection? So I'll delete now those. Any volunteer? Mesh equation for I current I1, for mesh current I1 by inspection.
Would it be 15V plus I1 times 5 ohms?
Just a second.
Sorry.
Would be, go ahead.
So 15V plus I1 times 5 ohms.
Isn't it minus 15, Patrick?
Oh, yes, yes. For
Minus
the
15, okay.
plus and negative. And then plus I1 times 5 ohms.
Right away, add all the resistors that I1 is going through.
Oh, 5
5
plus 10 ohms.
plus 10. This is I1.
And
And
then plus I3 times 10 ohms.
is it plus I?
I3.
Is I1 and I2 going in the same direction or opposite direction? In 10 ohm, for the 10 ohm.
Same direction.
Opposite.
They are opposite because I1, if don't let the same orientation clockwise confuse you. Although they both are clockwise, however, I1 is going this way and I2 is going this way, right?
Also, sir, can we get this equation that I1 minus I2 is equal to 1? Because the current in the middle branch is 1 ampere, because it's 10 ohm resistor and 10 volt.
No, no, no. You
ion.
cannot go this way. No, no, no.
Oh.
You cannot take the voltage and divide it by the resistor because it is connected to it. No.
Okay.
This is completely wrong. We're writing the mesh equation now, and we need to organize our thoughts and understand how to write it. Right. So back to Patrick. So we're done with the 5 plus 10 I1.
Yes.
Now we come to the shared resistor that is 10 ohm.
Mm-hmm.
I1 going clockwise, however, this clockwise for R10 means going from the top toward the bottom. Is this right?
Yes.
What about I2? Although it is clockwise as well, but clockwise for this 10 ohm would means going from the bottom toward the
Up.
up. So do you see I1 and I2 for the case of 10 ohm in the same direction or opposite direction?
Opposite direction now.
Then we write it here, we put here minus
Based on orientation.
based on being in the opposite direction. Because your reference is I1. Your reference is the mesh that you
Right.
are writing the equation for. This is your reference. You see I2 going now in the opposite direction. That's why you write it as minus. So this one would be minus 10 I2. Are we missing anything else?
Would you be missing I3 as well?
No, no. Those capital ones are completely different. They're not mesh currents. Those capital ones, capital I's, are not mesh currents. So don't mix them with, those are not my mesh current variables, the capital I's that you're seeing. I'm
Sure.
in the 10 volt.
Okay.
Sure.
So I still need to write plus 10 equals to 0. Is that clear now, Patrick?
Yeah, it makes more sense. Thank you.
Okay, you're welcome. Yes, yes, Matthias, go ahead.
So are we emphasizing mesh or super mesh analysis here? Because I'm assuming you can use either.
No, you can't. we don't have a current source here that being shared by two meshes.
So that super mesh analysis only works if you have a shared current source.
Absolutely, yes.
Okay.
Okay. Now we're done with mesh equation number 1. I need someone to tell me how to write mesh equation number 2. Any volunteer? You can make a mistake, no problem. If you make a mistake now, it's not gonna affect. It's not. You're learning actually. Oh, okay. I have several here. Okay. Let's start with. Okay, Liam. -10, and then 10 plus 6 plus 4 I2 minus 10 I1 equals to 0. Yeah, that's correct. I have here Adam 10 I2 minus I1, that's also work, plus 6 I2 plus 4 I2 minus 10. You forgot this equals to 0. Okay, that's all right. I have Rabia here minus 10 plus 10 I3. It's I2, not I3. Okay, hold on a second. Okay, so don't mix again between those assigned currents to the branches and between your mesh current variables. Those are completely different. We will later on derive the relationship between those capital I's and my mesh currents, but they are not the same. They are not the same. Okay, so 6 plus 4 I2 plus 10 should be I2. I think that's a typo. Minus 10 I1 minus 10 volt equals to 0. And that's correct, except for the typo. To be honest with you, this is very good. This is encouraging. So let's write it here. Again, I have minus 10 because it's entering, and then I put plus, and then I add all the resistors that my mesh current that I'm writing the equation for. So I have 10 plus 6 plus 4, 10 plus 6 plus 4, I2, and then going in the opposite. So always keep in mind if they have if you have both mesh currents in the same orientation clockwise as this way here, this means they are in the opposite direction, right? If both are clockwise or if both are counterclockwise, they will be in the opposite direction. So here minus 10 I1 equals to 0. So those are the two mesh equations. Now, if you rearrange those two equations, so this is 1, this is 2, from 1, we have here 15 I1 minus 10 I2 equals to 5. Then from 2, I have minus 10 I1 plus 20 right? I2 equals to 10 minus 10 I1 plus 20 I2 equals to 10. So those are the two equations that you need to solve simultaneously. Okay. Right? So if you multiply this by 2 and add them, what do you get? 2 times 15 is 30. 30 minus 10 is 20 I1. 0 equals to 5 times 2 is 10 plus 10 is 20 and I1 is 1 ampere and I2 should be, so if this is 3 sub 3 and here for example, so what do I get? Now this equation minus 10 I1 plus 20 I2 equals 10. If you divide by 10, what do you get? Minus I1 plus 2 I2 equals to 1. Put, rearrange I2. I2 is 1 plus I1 divided by 2. So I2 is 1 plus 1 divided by 2 is also 1 ampere. So I2 is 1 ampere as well. Now we need to find capital I1 and capital I2 and capital I3. What about I1 capital? I1 capital actually is the same as I1, right? So it is as if you have the same quantity here. You have current flowing here, and you gave it two names. You gave it an I1. It's just the small I1, and it's also the capital I1. So I1 capital is the same as the I1 small. So here I have I1 capital equals I1 small. They're both going in that branch, having different names, which means 1 ampere. What about the I2 capital? I2 capital is the same as I2 small letter as well. So here I have I2 equals to I2 small is also 1 ampere, right? Now what about I3? If you write a KCL, you can see that KCL here at this node is going to give you minus I1 capital plus I2 capital plus I3 equals to 0, and I3 is indeed I1 minus I2, which means I3 is 0. Okay, I3 is 0, and this now basically should make things clearer for your colleague who jumped into a conclusion right away and said I3 is 1 ampere because 10 volt is connected to the 10 ohm. This is wrong. You can, as you see here, we found out at the end that I3 is 0. There is no current going into the resistor 10 ohm. Okay. Any question about this example? No questions. Okay, so let's move on. This is the solution as well as given to you here. Now let's look at this example here. This example has three mesh currents, as you can see, and we have a dependent voltage source. There is no difference at all between dependent and independent voltage sources when it comes to the mesh analysis. So we, for the circuit, find I1, I2, and I3 using mesh analysis. So if we want to write the mesh equation number one, now the variables have been assigned already. The directions of those mesh currents have been given. You need to write the mesh equations and solve the equations simultaneously. So mesh equation number one. Who wants to write the mesh equation number one? And again, don't mix between those currents, the currents for branches, for specific branches, and the mesh current variables. Don't mix between those different.
I'll try again, sir.
Yeah, go ahead.
Okay, so for mesh one, minus 24 volts plus I1 and then times 10 plus 12, and then minus I2 times 10, and then minus I3 times 12 equals 0.
See, now things became clearer. You became more confident. You know now what you're looking for. You know now two mesh currents that are from the same orientation, you know, clockwise or counterclockwise means opposite directions and the shared components. Now things became easier now, and you wrote the mesh equation right away, you know, by inspection, and this is great.
Have you to thank, sir.
You're welcome. 12. Okay, so we have now the mesh equation, the right one written, and I would like someone to give me the mesh equation for mesh number two. Mesh number two. Who wants to give me the mesh equation for mesh number two?
So can I try?
Go ahead.
Yeah, it is 24 I2 plus 4I2 plus 10I2
So
minus,
add them all, right? 10
yeah,
plus 4 plus 24
I2
I2, okay,
minus 10I1
minus 10 I1
is equal to 0. Oh, no. And there is also minus 4I3.
minus 4 I3 equals to 0.
Yeah.
That's correct. That's great. Next, who wants to do mesh equation number three? Mesh equation number three. Don't worry about the dependent source. Treat it exactly the same as an independent when you write the mesh equation. It's a KVL based. Go ahead. Who wants to do mesh equation number three? No volunteers?
I can go again.
Okay, since nobody, came forward, go ahead.
Okay, so I3 times 4 plus 12. And then plus 4 I naught. Minus 4 ohms times I2. And then minus 12 ohms times I3 equals 0.
Yes, it is extremely important to keep in mind how many components you have shared. This will, later on will let you verify if you have missed anything. So like mesh number 3, the one that Peter just did, he kept in mind that he has this one shared and this one shared, right? And then he had two components that I3 is going through, and he had one voltage source. So when he wrote them, and simultaneously he kept in mind the number of the variables or that he has to keep in this equation. So this is very an excellent way to verify if you have missed anything in the equation that you're writing. So those are the three equations. Now, when we wrote the third mesh equation, we noticed that because of this dependent source, we kind of introduced a fourth variable, a variable that was forced on us to include in the equation, which is I naught. Keep in mind, whenever you have a dependent source, there will be a variable that this source depends on. You can go search for in the circuit and write it in terms of your standard variables. For example, this is a current controlled voltage source. This is a current controlled voltage source controlled by I naught. I should go search for I naught in my circuit, and that's I naught, and come up with an expression or an equation that relates this I naught to my standard variable in mesh analysis. So what are the standard variables in mesh analysis? The mesh currents, those ones. Those the ones that I have written my equations in terms of. So I need to find the relationship between my I naught and those small i's. So let's see. If I go here to A and write a KCL, see this I1? This is my small I1, right? And this is and by the way, those are small as well. So that's why I have them here ready. So those are not capitals. Only I naught here is the capital. So this I1 is exactly this I1, but it's made such that, see, I1, I1 also, I1 goes in both of those resistors, and I have I2 going in the opposite direction. But anyway, this is small I1 and this is small I2. I can write a Kcl equation at A to find the relationship between my I naught and those mesh currents I1 and I2. So Kcl at A, I have my small I1 entering, I have my small I2 leaving, I have my I naught leaving equals to 0, and then I naught as I1 minus I2. This is the equation now, the fourth equation that's going to allow me solve those equations simultaneously. Now, if you substitute this I naught into here and rearrange those three equations, you are going to get three equations, three unknowns. Then you can start eliminating those variables and find and calculate for I1, I2, and I3. Okay, due to the time limit, the solution is given to you here. You can do it the way you want. once you come up with those with the equations, then you can solve them the way you want. And I think you have done that before in a previous math course. If you want, we can come back and revisit that example and solve it. But due to the time limit here, we only have 4 minutes. Let's see what we can finish here. Yeah, so this example here, you need to find I1 and I2. Again, I have a current source here, then I2 becomes known right away. So I2 now is minus 5 amperes. So one of my variables became known, and then I only need to write the mesh equation for the first mesh, which is, I can do it by inspection, minus 10 plus 4 plus 6 I1 minus 6 I2 equals to 0. Substitute I2 with minus 5. So you have here 10 I1 plus 30 minus 10 equals to 0. And then I1 becomes minus 20 divided by 10. I1 is minus 2 ampere. Okay, that's the solution as well. We have this example. Now, this is an interesting question just to show you how can a super mesh expand. Notice that I have a current source here that's being shared. I have a second current source here that's being shared. So in this case, my super mesh becomes this, right? You need to write one equation. You can eliminate this guy, eliminate this guy, and write the super mesh equation for those three meshes that are merged. Keep in mind that I1 only for the 2, and I2 for the 6, and I3 for the 4 and for the 8. So if you want to write the super mesh equation, it would be 2 I1 plus 6 I2 plus 4 plus 8 I3 minus 8 I4 equals to 0. So this is the super mesh equation that includes all those three meshes in one equation. So again, 2 ohm is for I1, 6 ohm is for I2, and 4 and 10 are for the I3, and then you have 8 being shared. You need not to forget this one. Now here you have two, look at the binding equations. So if this one is the I1, small I1, and this one is the small I2, you can write KCl at P, where I1 is leaving, I2 is entering, 5 ampere is leaving. So this is the first equation, which is I1 minus I2 equals to, or let me put it, I2 minus I1, I2 minus I1 equals to 5. So this is the first binding equation. For this one, again, this is I3, right? In this branch, only this variable I3. In this branch, only this variable I2, write KCL at Q. You have I2 leaving, you have I3 entering, you have 3I0 entering. So this is my second binding equation from that shared current source. And then you need to write the mesh equation for mesh 4 here. So we have here mesh equation as 8 plus 2 is I4. So this mesh equation for mesh number 4, right? Plus 10 minus 8 I3 equals to 0. So this is the mesh equation. Now let's count the variables. How many variables do we have? We have 1, 2, 3, 4 variables, right? 5, I naught. So we have I1, I2, I3, I4, and we have I naught. Now this I naught, you need to write an equation. Where is I naught? This is I naught. Notice that this I naught is minus I4, right? So back down to 4 equations. So we have one equation, 2, 3, 4 equations, 4 variables, problem is solved. Now for me, in this course, although I'm finishing in less than a minute. In this course, what I care about is how you formulate your problem from circuit into equations. Yes, the math is extremely important, and there will be uh, weight assigned for both. But in this course, the new thing you're learning is how to formulate circuits into equations. So the weight for the formulation is going to be higher than the weight for the calculations, right? So just keep this in mind. I'll stop here, and sorry we're 3 minutes late. We'll stop here and we'll continue in next lecture. We have probably maybe an example. Maybe we can go through one more example, and then uh, in the office hours or in the tutorials, you can see all the details for solving 3 simultaneous equations or 4 simultaneous equations. Okay, but once the complexity on in the number of the once the number of the equations increases, complexity increases, then you will notice that the bigger weight of the marks will be given to the formulation. Thank you so much and have a good day, and sorry for being 4 minutes late. See you
Sure.
on Thursday. Yes.
Can you go back to the previous problem for a moment?
Sure. This one.
Oh, no, the one before that.
This one.
Yes. The problem is we have an I naught for mesh free, and if we had free equations, that would leave 4 variables, and therefore you'd have an indeterminate system. But is it possible to set up oh, yes, that's what you did. So what we could do is, to solve this, you could set up a 4x4 matrix with 4 equations. And so what you have is you have 3 KVLs and 1 KCL.
At the end, it is the same. Believe me, it is the same. If you substitute this I naught in mesh equation number 3 and rearranged it, you are going to get an equation with I1, I2, and I3. No difference. And,
Okay.
and a constant.
So my concern again was you had with free meshes, you still have 4 variables, but then you can add an equation at node A to create the fourth equation.
Yes, of course. You need to find a relationship, an equation between your dependent source controlling variable and your standard mesh analysis variables, which are those small i's that we have them here. Make sense?
Oh, yes. Okay, thank you.
You're welcome. Okay. Have a good day.